Good evening or good morning, everyone, or good afternoon, wherever you may be. Welcome to today's IFHE webinar. My name is Yoshisa Hirayama. I will be your host for today's session. My background is in mechanical engineering, and my professional focus is on healthy indoor climates and thermal comfort. I have been actively involved with the Healthcare Engineering Association of Japan since 2013, and I serve on the executive committee of the International Federation of Healthcare Engineering. IFHE brings together healthcare engineers and professionals from around the world to share knowledge, advance best practices, and support better healthcare environments globally. So today's IFHE's webinar is proudly sponsored by Mazzetti, an employee-owned engineering firm known for its long-standing work in healthcare, sustainability, and integrated building design. We sincerely thank Mazzetti for their support of today's program. Before we begin, I would like to note that this Zoom's webinar offers closed captioning and live subtitle translation into multiple languages. You can enable this feature using the caption or translation option at the bottom of your Zoom screen. That's the circle with the three dots. So if you click on those, you can choose the language for your subtitle. So we also encourage you to submit your questions at any time using the Q&A feature below. We will address as many questions as possible during the discussion period at the time of the presentation. So now it is my pleasure to introduce today's speaker. We're joined by Peter Dushansky, Managing Director of Glass Curtain. Peter has led multiple industry firsts in high-performance curtain wall systems and is frequently a frequent international speaker on facade design and building performance. Today, Peter will share lessons from the mental health unit expansion at Whitehorse General Hospital, exploring how next-generation glazing and curtain wall systems can perform in extreme cold climates while improving durability, life cycle performance, and patient outcomes. With that, please join me in welcoming Peter Jasensky.
Wonderful. Thank you. Thank you all very much for having me back. Once wasn't enough. It's rare that I get this opportunity to do two presentations in the same day. And those of you who are just kind of suckers for punishment and are for some reason back again on the same day, well, this one is going to be worth it because now we got all the bugs out of the way this morning, and now we're riding all nines. So thank you all very much for joining today, and for the lovely introduction. As I will just share my screen here, and we did a tech run, so this is gonna work because technology is easy, right? Technology is easy. Look at that. Look at that. All right. So yes, thank you again. Wherever you guys are in the world, it's fantastic to be able to share this with a global audience. So I wanted to extend sincere appreciation for the invitation today. And thank you also particularly to Steve Reese, who for making this opportunity a reality. Of course, Steve was online this morning. Steve, I hope you're doing something more interesting, like playing tennis this afternoon. But it's a pleasure to speak with you here today. Again, as mentioned, my name is Peter Dushansky, and I am the managing director of Glass Curtain. And we're North America's leading manufacturer of fiberglass framed curtain wall systems. And since 2013, we've actually had the pleasure of an opportunity to work closely with leading architects, building science engineers, and client teams across North America, particularly in healthcare, on buildings where performance really matters. So buildings that don't just need to meet the base building code, but need to represent durable, long-term investment on behalf of public and institutional clients. Buildings that are striving for performance on 50 and 100-year timescales and beyond. So today, we're going to focus on a very specific case study within this broader conversation, one that's, of course, particularly relevant to the IFHE community, and that's healthcare buildings, of course. And specifically, as Yoshi kindly mentioned, we're going to take a deeper dive into the new $33 million Whitehorse General Hospital Mental Health Unit expansion as our case study for today. Because, of course, while we can all learn from each other in terms of global best practices in many aspects of healthcare engineering, when it comes to building envelope design, that's the exterior of our buildings in particular, we need to understand and adapt to fundamentally regionally specific realities. What works in the context of hurricanes in Florida isn't what works in the context of floods in the Philippines, any more than it is the winters in Fargo, North Dakota. And while there's certainly more common ground and overlap in interior design and engineering across these geographies and climate zones, achieving that perfectly pleasant 20 degrees Celsius or 68 Fahrenheit for our American friends interior environment with the all-important Goldilocks zone interior relative humidity of 40 to 60% requires that the building envelope adapt to its specific geographic conditions. And in mental health environments, especially so, where access to daylight, views, and connection to nature becomes even more critical, as mountains of peer-reviewed research attest to. The amount of time people spend inside these types of facilities is often longer than other types of care. And the environment they're in, that mental health patients are in, has a direct and really meaningful impact on how these spaces are experienced and to the ultimate patient outcomes. So in these environments, there's a very rational, very reasonable, even very empathic or empathetic push by design teams towards more highly glazed facades, more openness, more transparency, more daylight, all good things. But in cold Arctic climates, like we have in Northern Canada, this and in many northern parts of across the world, maybe you guys are in Finland right now, and you can commiserate, or in Siberia for that matter. But this all too reasonable desire creates a distinct tension in these environments because increasing the glazing ratio, which is of course has all the benefits that we know for patients, also increases exposure, thermal bridging, and condensation risk, not to mention much higher energy costs, which means that we now have to balance a few things that don't naturally align. We need daylight and visibility to maximize patient well-being, but we also need the building envelope to perform under prolonged stress and in a manner that maximizes long-term operational value. So that's what we're really going to focus on today. How can we have our cake and eat it too? Or for our French-speaking friends, and of course, I know you guys are based in Geneva, so I'm sure you'll excuse my French. Comment peut-on avoir le beurre et l'argent de beurre? Right? Which of course, shows you how funny French is, that French, people are obsessed with butter. And British people are obsessed with cake because, in cake, it's how can you have your cake? In English, it's how can you have your cake in it too? In French, it's like, how can you have the butter and the money for the butter? So, I don't know what that tells you about the respective cultures, but I think it says something. So back to Whitehorse. Let's set the stage. Starting with where on earth is Whitehorse, or where on earth is Carmen Sandiego, or this place that we're talking about? So as we can see on our map here, Whitehorse is just above 60 degrees north latitude, which actually is the line that delineates between the northern territories in Canada and the southern provinces of Canada. There's 10 provinces, 3 territories. And for reference, down here we have Vancouver, for example. Here's where I am, actually, in Edmonton. We have Ontario, where we have Toronto. We have Montreal, Quebec City, these kinds of places, of course, across this enormous country. And it is a vast country, and that cannot be underestimated. And as some of you already know, it is actually the second largest landmass of any country in the world, sparsely populated at that. And what this translates to in practical terms, especially in the northern regions, is not just cold weather, but sustained cold weather over very, very long periods. Winter temperatures regularly reach minus 40 degrees Celsius, minus 50 degrees Celsius, and remain there for month after month. And one way to understand and sort of quantify this magnitude of this geographic stress on the building envelopes is through annual heating demand. And in Whitehorse, we see that they're experiencing 6,200 heating degree days annually, 6,200 heating degree days, compared to just 3,000 in Vancouver, 3,800 in Toronto, and actually still 5,200 where I'm located in Edmonton. But still, more than double Vancouver. Even relative to other major Canadian cities, we see that we're dealing with a huge amount more heat loss through the building envelope. And again, this tells us that it is not an occasional condition, but a continuous one accumulating over time. But even this sounds like an extreme situation. Even this doesn't even paint the whole picture. It gets more extreme than that. Because unlike other major Canadian cities, Whitehorse is not connected to pipeline natural gas networks. So for heat, this is what heats most cities that are not electrified, don't have electrified heating ventilation systems. Most are running on natural gas, and this changes the entire economic structure of how buildings operate and are designed. So in Vancouver, which actually isn't even that far away from Whitehorse, at least in the context of ginormous Canada, there's a relatively mild climate combined with access to low-cost hydroelectricity, which is cost-stable over time. And even in Edmonton, where the climate is certainly cold, we get, minus 20, minus 30, minus 40 for sure. There's direct pipeline gas access. So commodity prices are relatively low and relatively predictable. But in Whitehorse, not so lucky, right? Heating is typically is provided by propane and fuel oil, both of which have to be transported on trucks. There's no pipelines, there's no trains, trucks. Every single ounce, every single liter, every single gallon of fuel has to be driven on a truck. Huge distances without the advantage of pipelines, which means instead of scaling with natural gas prices, which are relatively stable, as it does in most of North America, energy prices in Whitehorse scale with crude oil prices, which, as I'm sure you've noticed lately, are volatile to say the least, and actually kind of up and to the right. They're yo-yoing, but they're kind of going up and to the right, and as we see at the pumps, for those of us driving non-electric cars. And so, hey, this is one more reason to have an electric car these days. And I'm grateful to have one as well. But this sourcing discrepancy, for energy, for heating in particular, in the Whitehorse area, becomes, again, even more impactful over time with oil shocks, with oil market volatility. And this is something that has to be really intentionally managed in ways that many markets don't have to consider, or have the luxury of not considering, really. So as a result of these dynamics, the total energy cost in Whitehorse can be up to 10 times higher than what you would see in a major city like Vancouver. And again, this gap is not static. Over longer time horizons, it can actually widen, because connected cities benefit from stable natural gas supply, but propane-based systems are exposed to transportation costs, weather differences, fuel price fluctuations, wars on the other side of the world, and other supply chain constraints. And in fact, over 20, 50-year life cycles, and that's not really unreasonable by any stretch of the imagination, total operating costs are easily tens of millions of dollars more in additional financial burden compared to major urban centers, which is obviously not a marginal issue and really becomes a defining factor in how these facilities are designed, funded, and maintained. And this is where the conversation shifts, because at this point, efficiency is not just about reducing energy use for a very sort of sympathetic sustainability objective. It's a foundational matter of risk management and long-term operational viability. Every unit of heat that leaves the building through the building envelope has to be replaced by expensive and uncertain energy supply in the future. So the building envelope isn't just some pure aesthetic architectural expression, much less a complete afterthought. It has to be holistically considered within the cultural and geographic context that it exists, which is why in a place like Whitehorse, facade design is so primary, so important, but that doesn't make it easy. And so we can see how this doesn't always go so well, right? So historically, the way that but of course, people try to fix this over time, with one band-aid or another. And historically, the way the industry has improved facade design, try to maximize some window to wall ratio while still maintaining some level of thermal performance, is to improve the glazing performance, right? It was the glass, the IGUs, the insulated glass units. And in most climate zones, that works pretty well, because you can we've seen huge advancements in the last 40 years when it comes to IGU performance. We've gone from single glazing to double glazing to triple glazing, low E coatings, warm edge spacers. you name it, vacuum insulated glasses, films, coatings, there's been huge advances in center of glass performance for IGUs for glass. Anywhere upwards of R8, R10 is achievable. Which are U values of 0.6 to 0.7 watts per square Kelvin, or for again our American friends, 0.1 to 0.125 BTUs per foot square Fahrenheit. That's great. That's fantastic performance. And again, there's all of these other kinds of technologies. I didn't even mention electrochromatics, and more and more. We've made huge advancements in the last couple of generations when it comes to glass performance. But when you look at the glazing system in its entirety, we're not just dealing with glass, right? There's the frequently overlooked framing that holds the glass in place. And in this arena, we can see that the same level of innovation when it comes to framing, we have not seen, has not carried through, right? We have not seen the same level of investment, the same level of material innovation that we see in glazing. And it shows when we look at a whole system performance basis, because even if we have, a center of glass value of R8 or R10, the whole system, when we factor in the framing, which is a conventional aluminum frame, right? Aluminum is, anodized aluminum is conventional framing material. When we factor that in, we have maybe R2, R3, maybe R4 at best. So that center of glass, is really dragged down by the frame performance. It's basically half the overall level that it could be. So in thermal terms, this means that the frame is obviously disproportionately responsible for heat loss to the facade, and that the frame is acting as the primary thermal bridge by a massive margin, especially as the glass gets better and better. So we can quantify this and we can look and say, okay, well, the frame is roughly 10 to maybe 15% of the facade area. But again, it can account for half of the total heat loss, even though it's such a small, relatively small area. So it really dominates the overall thermal performance, especially in colder climates, which probably makes sense from a material science perspective when we look at what we're actually using. And that's with aluminum in particular, which is one of the most thermally conductive materials on the planet. It conducts at 200, over 200. You can look up the material physics tables, right? Over 200 watts per meter squared Kelvin, which allows the heat to move through it very efficiently, which is why we use actually aluminum for a lot of wiring. Older homes, before we had copper wiring, aluminum was quite typical. It was a big fire hazard, obviously. You'd rather not have aluminum in your walls. You'd much rather have copper for fire risk. But we still use it for a lot of heating and ventilation systems, and so it's still very much in use. Of course, we'd rather not use it for building envelope materials, especially in colder climates, because instead of heat flowing evenly across the facade, aluminum will force the energy to be concentrated at the frame, particularly at the mullions, corners, and connection points, where the conductivity pathways are continuous, and this translates into surface temperatures. And when you translate it into surface temperatures, the difference is stark and easily measurable as well. Under cold climate conditions like we have in northern regions, interior surface temperatures at the frame and at the edge of the frame can be more than 10 degrees colder than the glass surface, creating localized drops that directly determine whether or not the system, and again, these are systems that are composed of multiple components, not just glass, right? These are systems composed of framing and gaskets and systems, right? And when any one part of that system is weak, the whole system, is vulnerable, right, to failure. And so if you have a 10-degree difference and that drops below the dew point, especially in healthcare environments where we have interior relative humidities of, again, that sweet spot, 40 to 60%, right, per ASHRAE and Harvard Medical Institute. And so if the dew point falls below 9 or 12 degrees Celsius, the interior surface will see condensation begin to form. And in a climate like Whitehorse, where exterior temperatures can readily reach minus 40, minus 50, and remain below minus 30 for extended periods, these difficult envelope conditions are not short term. And so hopefully, we're starting to see why facade design is such a hard problem to solve. How do we have our cake and eat it too? And if that wasn't hard enough, it gets a little bit more complicated before we have the solution, or one of the potential solutions at least. And that's because buildings are dynamic, right? They're living, they're breathing, they're alive in their own way, right? And with thermal differentials between you know, 60 to 70 degrees between interior and exterior environments, right? If you're trying to maintain 20 degrees Celsius inside and it's minus 40, minus 50 outside, you know, typical aluminum framing has a further challenge, and that is actually expansion and contraction, right? And so aluminum, again, you can look up these on the physics tables. This is, you know, you know, just idle speculation. The coefficient of thermal expansion for aluminum is 23 times 10 to the 6 per degree Celsius. What does that mean? It means that the aluminum frame is actually moving at twice the rate of the glass it's holding. Right? We imagine that these things are static together, or that they're going to move in concert. Right? They're going to move one with the other. So if they move left together, they move right together, they expand together, they contract together. These are different materials, and they're going to have differential rates, especially when you're dealing with glass and metals, right? And so, you know, compared to, you know, next generation fiberglass, which is actually mostly glass, which is moving at basically the same rate, aluminum is moving at twice the rate. And over time, this has, frankly, relatively catastrophic effects in typical aluminum systems. Because, you know, if we put this, you know, in practice, and, you know, given a standard span, you know, a standard aluminum mullion of, say, you know, 3 meters in length, call it, you know, 9-10 feet in length, pretty standard for a healthcare curtain wall application, exposed to a 60-degree temperature swing, we can see dimensional changes of over 5 millimeters, which is 3/16 of an inch between the warm states and the cold states. By comparison, fiberglass with a coefficient of expansion of just 10 to the minus 10 to the 6 compared to 23, 10 to 20, you know, so a little bit less than half of the difference in thermal coefficient, will actually move only about 2 millimeters. And those numbers might not sound like such a huge amount, but when you factor in unusual geometry, system geometry, locations of interior elements such as radiant heaters, curtains, beds, other furniture, and then you wash, rinse, and repeat just a few thousand times, all of a sudden we have cyclic loading of sealants and gaskets that very soon degrades from its initial state. You thought the initial state was fine? Maybe it was. But is that state maintained over time? Or does it degrade, and how quickly does it degrade, right? The more expansion differentials in expansion contraction you have, the more quickly we will have system degradation. And as I'm sure you know, maintenance cycles can be very long, which means that, you know, sub-acceptable standards of performance will be more the norm than certainly desired. And of course, you know, what happens when you have these differentials? Well, you're going to have, you know, degradation of seals and gaskets, resulting in air infiltration, moisture ingress at the same interfaces where thermal performance is already reduced. And this is in, you know, a healthcare environment with vulnerable populations. And in a former life, I actually majored in immunology and infection at the University of Alberta. And I don't even advertise that to everyone, but, you know, I feel like we're in good company here. So I can more than appreciate the importance of sanitizing protocols and the enormous efforts that go into protecting immunocompromised patients. So trust me when I say the last thing you want is a leaking building envelope, even though it's unfortunately all too common. At an operational level, what does a leaky building envelope translate into? Well, unfortunately, probably some of you already know this, but of course the answer is shorter and more expensive maintenance periods, higher energy costs, more stress on heating and ventilation systems, premature failure of heating and ventilation systems, higher energy costs, because now you're heating and cooling the outdoors as well as the indoors. Not to mention, hey, what's the whole point of healthcare? Worse patient outcomes. That doesn't sound great. And again, from a maintenance perspective, constantly babysitting the facade, mopping up condensation, and making sure patients and visitors don't use window blinds, especially on cold days, so that the air can actually circulate over the facade. And, you know, keeping the frames and glass dry. When really, oh my goodness, these systems should just be doing their jobs, right? Out of sight and out of mind. When glazing systems are not properly designed and specified, and repairs are finally, unavoidable, all too soon, I might add, of course, access to facade systems is then going to be even limited, because even targeted interventions require complex coordination with ongoing clinical operations. And frankly, no one needs that headache. So a truly functional facade, one properly suited to its geography and natural environment such as this, will maintain the highest levels of air tightness, thermal continuity, and surface temperature at critical interfaces, month after month, year after year, and decade after decade. Understood holistically, performance cannot be simply defined by nominal system values or short duration testing, or never mind just cheapest initial cost. Rather, it unequivocally has to be understood as the ability to handle continuous cyclic movement without loss of integrity and to maintain durability and quality, driving value and patient outcomes for generations to come. What this means in healthcare, when the ideal behavior plays out, this impact extends well beyond the building envelope itself. Because these spaces are, after all, not just technical systems. They're environments where both patients and staff, lest we forget staff, spend extended periods of time. And what determines success for these groups, these various groups? Whether, well, we can calculate a few different ways. How low is staff burnout rate? How short are patient stays? How effective is treatment? And we can look at the substantial body of public health research and healthcare research more broadly. And we can see very clearly that access to daylight, thermal comfort, and stable interior conditions are critical factors linked to these measurable outcomes. For example, studies have shown that patients in rooms with access to natural daylight experience reductions in lengths of stay by up to 10% or more. And think about what that's actually worth to the healthcare system or your facility if you could reduce patient stays by fully 10%. Furthermore, particularly in mental health environments, access to daylight and views is consistently shown to reduce stress levels for patients and for staff, improving patient outcomes and reducing staff turnover. So on the staffing side in particular, we can see that higher productivity in facilities with better daylight conditions, which of course can have meaningful financial impacts at the facility level, because even just replacing a single nurse, never mind the actual, just replacing, just a like-for-like replacement can cost $40,000 to $60,000 easily when you factor in recruitment, training, and lost productivity for the transition. So, staff burnout is a real challenge, right? So the continuity of care is worth an immense amount to healthcare facility operators, not to mention patients who come to form relationships with their healthcare providers. So when we connect this back to the facade design, the relationship is clear. If the building envelope design limits glazing percentage in order to manage, say, thermal performance, this directly reduces access to daylight and views, which negatively affects patient experience and staff well-being. On the other hand, if glazing ratios are increased without addressing performance of the frame, as we've seen, which is the weak link, clearly, we'll begin to see issues as we've discussed already: condensation, maintenance, and inconsistent interior environment. So when we look at the facade in its entire context, we can see that it's really so much more than just another building component, another afterthought, and it's really part of the infrastructure that supports how the healthcare system functions, both in terms of patient outcomes and staff performance. And that's why consistency and quality at this interface is so critical. Now, up to this point, what we've discussed is, maybe nothing new, but, worth remembering as well. But the relationship between thermal bridging, surface temperature, and condensation had, arguably been well understood for decades. And the performance gap, even between glazing and framing, is not something that's really recently emerged. But despite this documented, measurable, and predictable sort of state of affairs, unfortunately, we actually do tend to see a lot of the same old quote-unquote solutions appearing in new buildings, largely because the way facade performance is evaluated doesn't always carry through into how that performance is experienced over time. So how can we do better? Well, let's look at our case study, which is the roughly 200,000 square foot healthcare building at Whitehorse General Hospital in Yukon, where we see that we have annual energy costs of about $2 million a year, which is not nothing, especially when we consider that a facility of the same size were to be located in Vancouver or Edmonton or other sort of major urban centers would actually only be about $500,000 a year. So that's a fourfold higher energy expenditure for the same building and doing the same functions. As we mentioned earlier, that difference is not really driven by electricity cost so much, because largely a lot of the hydroelectricity in Yukon in the 11 to 13 cents per kilowatt hour range, but it's really down to cost of heating, which at $40 per gigajoule, that's upwards of 10 times more than the, 6 to 7 or even less, dollars per gigajoule for natural gas in major connected markets, which means that both the demand for heat and the cost of supplying it are massively elevated in this environment. And under these conditions, even modest increases in heat loss through the building envelope, even modest degradations in facade performance, translate into measurable increases in operating costs over time. And we can actually do these calculations, right? So we do a net present value calculation, very reasonable 5% discount over again, a very reasonable 25-year period. We can see that Whitehorse General Hospital will actually spend $20 million more on maintenance, $25 million more on energy, and $200 million more on staff than similar buildings in major urban centers. So the facade performance is structural. The facade performance is critical to success in this region because it fundamentally shapes how the building will be funded, operated, maintained, and really its fundamental viability as a publicly funded institution, right? This is a completely publicly funded institution. There's nothing private about this, right? So as we can see here, the ruthless reality of how this building envelope system needs to be evaluated during the design phase on projects like this serves as a keen reminder and an opportunity for really all healthcare facility operators to think holistically about their new designs. Because in our healthcare facilities, even more so than other institutional building types, operating and staffing costs have such an outsized impact on the bottom line. And with more intelligently designed and specified facades, we can truly see that an ounce of prevention is worth a pound of cure. So how did Whitehorse General Hospital actually achieve its necessary objectives? How did it have its cake and eat it too? Well, with a little Canadian know-how and ingenuity. After all, necessity is the mother of invention, and Canadian glazing system manufacturers lead North America and even some of the world in some categories when it comes to frame design and technology, particularly with advanced composite materials like fiberglass. So in this particular case, the architect and design team specified the award-winning ThermaFrame 7 fiberglass framed curtain wall system with an overall thermal performance of R7, which is about 0.85 watts per meter squared Kelvin or 0.15 BTUs per foot squared Fahrenheit. And more importantly, this is not just the center of glass value. This represents the holistic full system performance, capturing behavior at the frame where a significant portion of heat transfer typically occurs. And since it's a fiberglass frame, we know it won't expand and contract basically at all over the time and thermal cycles. We know it's going to actually maintain that performance for decades to come, even in these subarctic environments. And uniquely for the first time, the fiberglass framing was actually also paired with Unicell Violite integrated blind assembly. So they're actually still triple glazed units, but between two of the lights, the inner lights, there was actually an integrated blind. This is a cord-free design for mental health patient safety, which also allows for solar control and privacy. And when installed together with fiberglass framing and integrated blinds, we have a dramatic improvement in the design and functional possibilities of the space, resulting in a more comfortable, condensation-resistant interior that's more durable, more airtight, lower maintenance, higher performance, and minimizes HVAC stress, and of course, improves patient outcomes. So the mental health unit at Whitehorse General Hospital was therefore able to actually achieve a pretty staggeringly impressive 30% window to wall ratio, which is day and night compared to the average in the region, which is 10% window to wall ratio. So I made this analogy earlier, and that's, in the days before curtain wall, when we had, mostly masonry buildings, every penetration through the building envelope was a structural penetration. So windows could only be so big. Frankly, cold climate architecture works the same way, but it's not structural, it's thermal. And so the ability to expand that window to wall ratio, to open up, to create more daylight is absolutely remarkable in terms of the quality of the space. And not to say the architectural expression, really the function, the daylight, and the sense of openness that's possible. And this supports patient well-being, not to mention staff quality of work environment over the long term. So we've covered quite a bit today. Starting with the environmental reality of a place like Whitehorse, which, maybe those of you who've never been to Whitehorse, but, maybe you'll go one day. There's pretty amazing northern lights up there. Very romantic. And especially the last few years, it's been incredible, this whole northern lights thing lately. But Whitehorse is a special place with special constraints. And the realities of its energy infrastructure, how the conventional facade systems do or do not work under this level of stress, and how this behavior translates into measurable impacts on energy use, maintenance, and long-term performance is noteworthy, is a case study, is worth sharing. And what this progression shows is that the building envelope is not operating in isolation, right? Its performance carries through into how the entire building is experienced. It's sort of like our skins, right? It's sort of the first thing you notice. And so, this translates into how the building is maintained and really funded over time. And it's critical that these are investments that we're making. So especially in environments where these stresses are continuous rather than occasional, we have to think, short term, medium term, and long term, right? All at the same time. In a healthcare setting, this connection between quality of inputs and outputs is as direct as it gets. This isn't just, an apartment building, right? We're dealing with critical and vulnerable populations here. And we can see that the decisions at the facade influence not only energy use, but again, daylight, thermal comfort, and ultimately how reliably the space performs over the full lifespan of the building, which isn't, we looked at the numbers, over just 25 years, it was, $25 million in extra energy. That's just over 25 years. It's extra $1 million a year just in energy, right? But this building will absolutely be in service for 50 years plus, right? Plus. And so the net present value calculation works into a stunningly good ROI for the incremental investment for a high performance, fiberglass frame system. Because glazing systems are typically the weak link. And frankly, even in high performance systems, they're still, fundamentally weak link, but there's a lot, no, they really don't have to be. There's a lot that we can do to make these systems better. So Whitehorse General Hospital demonstrates that when we consider holistically material properties, system design, and building use together, it becomes possible to support higher levels of transparency and daylight while still maintaining the levels of performance required to the specific climate. So instead of narrow trade-offs, we're able to achieve performance, durability, and operational alignment, all in a way that benefits the local community for generations to come. And with that, that was kind of short and sweet. I'd like to thank you very much for your time today and welcome any questions that you might have at this time. Thank you.
Thank you so much, Peter. Okay, here's a question from okay, can you read the question?
Oh, yes, perfect. Thank you.
Right.
What advice would you give to design teams in other cold climates who are just starting to explore high performance facade solutions for healthcare facilities? Yeah, I mean, reach out to myself or other manufacturers, to discuss how the sort of specifications work, because it really comes down to specification. And in a lot of these cases, we're dealing with government funded facilities or sort of publicly funded facilities, and the specifications have to be worded, in a very sort of open-handed way, right? You can't just say, oh, well, we only want a manufacturer X, right? You can't just sole source, even if manufacturer X happens to have the best, system in the world. So typically what we see are actually performance specifications, right? So it's not necessarily, you could use base of design as, say, manufacturer system X again, but the U value performance, I would say, is one of the big drivers. So if you're looking to specify U value performance of 0.85 or 0.9 watts per meter squared Kelvin overall framing glass, not just center glass, overall framing glass, that's a great way to sort of separate the wheat from the chaff and really get something of quality. And then you're basically going to be competing between, again, depending on the kind of system, there's, a great fiberglass system or even some of the better European systems can actually meet similar levels of performance as well. Your standard Conair or Lumicore kind of curtain walls will not be able to achieve that, which is great because they don't perform great long term for high humidity environments, especially in colder climates. So, really look closely at the spec, work with a spec writer, and work with the manufacturer. Lots of manufacturers are happy to do design assist, and help you work through, help you navigate what the best way is. Yeah, something we certainly do all the time, and I'm sure other manufacturers as well. So great question. Walt Vernon had another question as well. I've heard people advertise themselves as facade consultants. Is it worth hiring one of them? I think it certainly can be. And sorry, he just had a follow up. Is I worked at the first NREL zero carbon lab. Okay, great. And they obsessed over the window frame as a weak point. Yeah, that's because they are. It's like, and it's, I think it's worth obsessing over. What's the best possible frame we can use? Depends on the spans. It depends on your climate and the kind of spans you're trying to achieve. If you're just doing, for colder climates, fiberglass is pretty much optimal. You don't want PVC. PVC is absolutely the worst solution you can have. The middle solution is aluminum, and there are better different grades of aluminum systems. There's good, better, best. The standard aluminum is not great. European systems for aluminum are substantially better. And then there's fiberglass, which is probably a notch above that even. I wouldn't necessarily use like a wood frame or something like that either. So, steel maybe has some applications for very large spans, but for typical kind of healthcare, you're not typically doing those kinds of spans. So yeah, it is worth probably having a facade consultant or a building envelope or energy modeler. Energy modeler is great too. Energy modelers have a good sense typically of what kind of materials perform in what way within the holistic context. Like what an energy modeler can say, okay, if we switch out this window, this is the impact on heating and ventilation system. We can downsize the HVAC unit to this size if we have this window, or if we have this much windows, or if we have this little windows. And so either facade design or energy modeler can I think service that. So best frame is yeah, I would say fiberglass is obviously a great solution, but again, in colder climates, like you're probably not going to use so much fiberglass in Miami or something like this, right? Walt had another follow-up question as well. Operable windows, how does it impact facade design? Very much so, quite significantly. And we love operable windows. Who doesn't love fresh air? Most of the projects I would say that we do have operable vents or operable windows integrated into them. That can be more complicated in healthcare. I know that there are some constraints, and this there's a lot of tension I think between the maintenance people who just want to rely on the HVAC systems and the patients who really like fresh air. I don't know how to resolve that personally. I probably don't have a silver bullet for that. But that is, I would say more institutional buildings, so like university buildings that we do, schools, rec centers, other kinds of office buildings that we do, will more typically have operable vents. Operable vents can be more complicated unless you have them integrated, with automated timing and stuff with the rest of the building mechanical system for healthcare. But that's atypical from my observation, anecdotal observation in healthcare. Shading, great question as well. We did displacement ventilation at Stanford Medical Center. Very cool. We had to control solar gain, of course. How does window shading impact your thinking? Well, window shading is fantastic as well. Of course, you had a lot of glazing. You can have a lot of solar heat gain, especially in more temperate climates. You're more balancing. Your buildings are more cooling dominated more of the time. And so, but even in colder climates, your building can be cooling dominated to minus 10 degrees Celsius, right? Which is what, like 20 something Fahrenheit. Like your building can still be cooling dominated because you're just generating so much heat inside that you're still running the air conditioning basically. And so yeah, you want to maximize, especially if you have south facing, where maybe we have some southern hemisphere folks that when they're north facing windows. This is kind of cool, actually. I don't usually talk to folks from all over the world, but yeah, if you have north facing windows in the southern, if you're in Australia or New Zealand, yeah, your north facing windows will have to have more shading. And the rest of us, most of us, in Europe, North America, most of Asia, we're dealing with south facing solar heat gain. And yeah, shading is critical. Our systems certainly integrate solar shades on many projects to manage solar heat gain. Again, just depends on how much glazing you have and its orientation, of course. But it is important, and frankly, why wouldn't you have some shading? doesn't always have to tie back into the frame. It can be an exterior sort of structure as well, or substructure that sort of handles that dynamic load from the wind, especially for and from the dead load of the sunshaded shell. But it can also be integrated into the curtain wall. So yeah, so no, thank you, Walt, for the questions and for the positive comments as well. Glad you enjoyed. Um,
Yeah.
anyone else have a
Pe-
few bits?
Peter, I have one myself.
Please.
Actually, I work in the field of heating systems and indoor climate design. And, our first point of focus is facade and its thermal performance. And obviously it affects the overall quality of the indoor space.
Mhm.
Um, in Japan, we have up in the northern parts and coldest areas, it's let's
Mhm.
say -10 to -20
Mhm.
degrees outdoor temperature.
Mhm.
So, we have a thermal differential of what, 40 degrees? I
Yeah,
mean, obviously not as bad as 60 where you
but
work in.
still.
Um, Engineers and architects in Japan often say we the best or the better solutions are wooden frames or
Mhm.
PVCs, and you are
Mhm.
sort of against that. Can you maybe elaborate on that? Because some people actually think that PVCs are pretty good window frames in terms of thermal performance and costs.
Yes, so PVC is great on cost, but uh, it's probably the least durable solution you can think of. It expands and contracts wildly. So one, I mean, I guess thermally in a static dynamic, in a static sense, in a non-cyclic uh, sense, it's fine. It's fine year one. PVC is fine year one. PVC goes down a cliff year 5, year 10. It's terrible for thermal expansion contraction. You can look up the tables. You can look up the material tables, and it expands contracts like a yo-yo. It makes aluminum look stable. And aluminum's not that stable under sort of large differential conditions. So you definitely want to, I would say, avoid. I would personally want to, if it was my healthcare facility, I would certainly, that would be the bottom of my list. Wood has some applications. Wood has some other limitations as well. Wood's great aesthetically, right? Like we all like the look of wood, right? It's warm, it's inviting. You feel like you're part of nature. Don't get me wrong. Um, Wood is more limited structurally. It's not as strong. You can't do as big of spans on it. From a high humidity environment, perspective, it can rot, right? We've all seen old wooden windows rot. And of course there are treatments you can apply to that, but those are somewhat limited. And then it's also very limited when it comes to, I think we maybe touched on this earlier as well. If you have sort of more advanced, if you like sunshades, forget about it. Anything more structural, anything more demanding, like from wiring. If you have solar panels integrated, electrochromatic glazing, you need to wire through it. Door adapters. Because it's a solid frame, right? Any wood frame is a solid frame, whereas other materials are hollow tube frames, right? The hollow tube frames allow you to do a lot of interesting and useful attachments and advancements through here. So you can have you run wiring through there. You can have the spigots and the shear blocks, connecting there. There's all kinds of things you can do. So I'd say that's the other probably limit. Yeah. So wood is an interesting material for sure. You also have to be mindful of combustibility of wood framed products as well. PVC, I also imagine would do very poorly in a fire. To be determined depending on the context as well. Most PVC systems have to be heavily reinforced with metals to have any structural strength because they're actually very weak structurally. So you often have to reinforce them with aluminum or steel to get them to even span, a couple meters. And so, yeah, I mean, they have their application for sure, but compare, on a holistic basis, especially for those colder climates like you have in northern Japan, for sure. I would say fiberglass is a holistically superior option for those situations.
Thank you. Previous in your previous presentation, there was another question raised by Rory Carroll. How does glass fiber perform under the high UV conditions over time?
great question as well. And so happy to discuss that again. So there's a threefold protection for that, because of course we've all seen old canoes or old boats or something that end up overexposed in the sun. They start to peel or flake a little bit, right? We certainly don't want that, and we don't have that with high performance fiberglass curtain wall. And that's because there's three things we're doing. So number one, this is not exposed to direct sunlight, right? So we have a frame, interior frame, we have an exterior snap, we have a glazing line here. The light is coming through, and it is filtered through 1, 2, even 3 low-E coatings. So you don't actually have direct, at an angle as well. So you don't actually have long-term continuous. It's always filtered light, and it's always at a sort of oblique angle. Secondarily, we can and do add to the fiberglass resin itself UV resistant resin components into the matrix, into the composite matrix. And then third, last but not least, is painting. Actually, so we actually do a very hardened, factory applied paint to the exterior surface of the frame. And this paint, obviously eliminates all UV exposure. So even any potential, even if you got a scratch or something, you really are eliminating. You can always touch that up, but you really are with a painted surface. And we paint this surface to AMA 624 standard, which is actually an exterior paint standard designed to handle 5 years in the direct Florida sun, which of course it will never see. So the paint standard is definitely overkill for the application. So yeah, those kind of the top 3 ways.
Okay, thank you. Are there any other questions? Finally, perhaps one more question from the previous session. Can you give a sort of a cost comparison between fiberglass frames and the typical aluminum frame systems? I'm sure everybody's more familiar with aluminum systems.
Of course. No, happy to discuss that. So it is certainly a premium for fiberglass. Higher performance, higher premium prices. You sort of get what you pay for, but the ROI is fantastic. Very short, and especially in colder climates. We're dealing, it might be months, maybe even a couple of short years, and you're dealing with buildings that are going to be around for decades, if not generations. And so we're typically looking at, in a place like Whitehorse, the premium might only be 10%. In a larger market, it might be 15%, maybe 20%, could be 30%, depending on a bunch of different factors: sizing, scaling, location, geography, this, that, and the other, but not typically much more than that. And again, it's fantastic and great ROI, especially in a colder climate. It pays for itself. Again, like we're talking about $25 million over 25 years. Incremental energy cost. Okay, so let's say just to make a number, let's say you spend an extra $1 million, on the curtain wall. You get that back in the first year, right? And it's like, and then you're just cashing checks, thereafter. And no, obviously not literally cashing checks, but if your facility is solvent, then you get to keep operating. And so, the alternatives are, and you have a beautiful daylit space. The ROI is pays for itself, and then some.
Right. Okay. Thank you very much. Thank you, Peter. I think that brings us to the end of today's webinar. On behalf of IFHE, thank you to everyone who joined us. I hope you were able to get a good insight into the importance of facade engineering, particularly for providing healthy, comfortable indoor space and keeping energy costs down from this Peter's inspiring presentation. We'd also like to extend a sincere thank you to Mazzetti for sponsoring today's webinar and supporting our ongoing education in healthcare design and performance. So before we sign off, we're excited to invite you to IFHE's next webinar, Future-Proofing Hospitals with Geothermal Heating and Cooling, presented by Jonathan Hernandez, Director of Geoscience at Brightcore Energy. We hope you join us next month. Thank you again, and have a great rest of your day or evening where you may be. Thank you.
Thank you.